Mensuration, the topic which includes diagrams and shapes and the interesting solids which we take into consideration in daily life. So what is mensuration? Mensuration is a topic which includes the most important topics, the connected words which we identify in mensuration as area and volume. The minute mensuration comes into mind, these two are the words which come immediately into the mind, the areas and volumes. So when do we find the area and when do we find the volume is the biggest question in case of the three-dimensional mensuration concepts. What makes me find the area and what makes me find the volume is what we need to understand. So finally, we just try to take some example problems to identify whether the situational problem is related to finding the area or the volume of the given problem. So initially, let me start with the canvas used for making a tent. If my problem is related to the amount of canvas I require to make a tent, then immediately what shoots in my mind is about finding the area, is how I understand the situational problem. The canvas I use for making a tent is related to area, therefore this problem is exclusively used in identifying the area of the given situational problem. Similarly, if I take, say, gas filled in a cylinder, then immediately these situational problems make me remind of the volume but not the area, because when the gas is filled in the cylinder, we measure it with respect to the volume. When we take the amount of canvas for making a tent, we measure the canvas through the area, is how we need to identify whether the problem is related to finding the area or the volume from examining carefully the given situational problem is very important. So gas filled in a cylinder is identified to be the volume related problem out here. Let's take some more examples in identifying here. Laying down the road or construction of a road is clearly a problem related to the surface, that is area. Or if I take filling up the petrol in the tank is a problem related to volume, because when I fill the petrol in the tank, I measure it in liters, or I say I want 5 liters of petrol to be filled, but I don't say I want this much area of petrol to be filled in the petrol tank. Therefore, laying down the road is a problem related to area. Similarly, filling up of petrol in vehicle tank is nothing but a problem purely related to volume, etc. So this is how we try to understand or analyze or especially visualize on how we can identify the problem for finding its area or volume. Remember, it's very important that mensuration is a topic which includes visualization of objects, because when I say I want to find the length of the bridge or I want to find the area of the complete petrol tank, then I don't assume going out and measuring the entire petrol tank, but I visualize and then take the dimensions to find the respective areas and volumes using the visualization concept. Therefore, this is very important before we start the actual topic of mensuration. Identification of area and volume is the most important concept. So finally, the learning outcome here is that we identify that situations decide whether the given problem is about finding the area or volume. So finally, my learning outcome in case of this session is that it's purely the situations which decide whether the given problem is about finding the area or the volume, is what is the interaction of mensuration connected with area and volume. Now, as we have seen mensuration connected with areas and volumes, now there are so many different shaped objects in this world. So in the universe, you find different shapes which have their own definitive measures. Now say for example, I take the most simplest example of a pencil. I see that it has a sharp object and then the rest of it is flat and then it is bulged in the bottom, or sometimes it might be flat. Now this makes me understand that there are different shapes out here. If I separate the different shapes, I first have this shape out here and then this comes out in this form, and then finally if I separate in this. So these three different objects, when I separate from this, when combined together forms a pencil, which we most oftenly used for graphing on the graph sheet. So different objects are combined to form a definitive object called the pencil. Now say for example, I take a real life object, say we all know that this is a funnel. So in case of this funnel, I see that I have one of the shape out here which is exactly separated from the other shape here. So my visualization makes me understand that there are two different shaped objects in this combined object. One is this curved surface object which is called the cone in its mathematical meaning, and the other is a cylinder which I find here in as the thin part. So a cylinder and a cone makes a funnel is how I understand. To take with the diagram, I have this in the shape of this, so that this funnel when separated gives me a cylinder sort of shape, and then the bottom part gives me a cone sort of a shape, is how I understand the object in its own definitive manner. So there are different objects. Say for example, I take one more object for better understanding of how the combined structures are understood. Now we all know that this is a test tube which we most oftenly use in the biological laboratory, most oftenly. So in the sciences laboratory, the test tubes are used very oftenly, so you're all well aware of this. Now we know that this has a cylindrical surface until here but bulged. That means I have a cylinder and the other part is a hemisphere which I find, because this is part of the sphere. Therefore, if I visualize this object, I understand that a test tube which is generally flat but bulged in the bottom makes me understand this can be separated as a cylinder and then a hemisphere, which I get from separating the two objects. So finally we see that a test tube which is separated into the cylinder and the hemisphere, or a pencil which is separated from the top, the middle and the bottom, or a funnel which is separated with a cylinder and a cone, is how we visualize the combined structures. And separating them and then finding each of the areas and volumes would be easy, because each of the cylinder or a cone or a hemisphere have their own definitive properties. Therefore, mathematics in mensuration have identified some standard objects like the cuboid or a cube or a cone or a cylinder, or we have different shapes like pyramids, etc., which are said to have definite areas and volumes. So let's see some standard structures and their areas and volumes respectively. Now there are 6 standard solids which we are going to discuss in mensuration connected with areas and volumes. So these are the 6 standard solids which we usually apply in finding the volume or area of any object with the combined structures, as we have seen in the previous case of a funnel or a test tube or a pencil, where they are divided into different structures, each with their own standard structure as a solid. So let's take some of the standard solids which are cuboid and a cube, because both have their own definitions coming out here. Next is, we have cube or cuboid as the first case, and then I have cylinder, then I have a cone, then I have a prism, then I have a pyramid, and then I have a sphere. So using these 6 basic solid structures, I am going to construct the multiple combined structures where the areas and volumes can easily be identified for the standard solids. So let's take each of the standard solid separately and identify the dimensions and connect it with areas and volumes. To start with cuboid and a cube. Now to start with cube and a cuboid, initially the first solid structure is a cuboid, which we all know that is in the shape of a box. So when I draw a cuboid, it is in the shape of a box, where this is length, this is width, and this is height, is how we understand the cuboid. Let's take a cuboid which is in the form of a box. As I can see here, this is a cuboid because it is exactly in the form of a box, a rectangular box which has each of the length is L and the breadth is B and the height is H. Together make the dimensions close to form a cuboid. Now in case of this cuboid, I identify 2 types of areas which I am going to discuss here. Now in case of a cuboid, I have one is the lateral surface area, or it is also called the curved surface area in case of curved objects, and the total surface area is the total of the entire area of the box taken in any face or any angle of. What is the lateral surface area and how is it different from the total surface area is the biggest question out here. Now when I discuss about lateral surface area has its own definition. Say for example, I take a cuboid which has the length L and the breadth B and the height H, as I taken L, B and H. For this box, I wanted to find the lateral surface area, implies I want to find the area which is considered horizontally along the horizontal axis. So this is said to be the lateral surface area. The top and the bottom areas are not considered when we take the lateral surface area along the horizontal axis. Therefore, if I add this area with this and this and this, I get the entire lateral surface area. So therefore, initially to start with finding the front face of the area, which is this, is LH plus similar area of LH is exactly equal on the opposite side, which is also LH, is what I get for one part of the lateral surface area. Now coming to this, the other region of the lateral surface area is this, where this is B and this is H, as can be seen with B and H. Therefore, when I add this with this, I get 2 rectangles which are added where area of rectangle is base into height plus base into height, which are separated on the two sides opposite to each other. So the lateral surface area is finally obtained to be 2LH plus 2BH, which gives me 2H into L plus B, is what I get. The lateral surface area of a cuboid is 2H into L plus B. Now, when it comes to the total surface area, is nothing but the lateral surface area plus top surface plus bottom surface, is how I understand the total surface area. So therefore, since the total surface area is lateral surface area plus the top surface area and the bottom surface area, therefore I get this to be the lateral surface area is already obtained to be 2H into L plus B plus the top surface, which is a rectangle with the length L and the breadth B, as can be seen as L and B, gives me length into breadth plus length into breadth, one with the top and one with the bottom, giving equal areas of rectangles on the top and the bottom. Therefore, when I simplify this further, I get this to be 2H into L plus B plus 2LB. Therefore, when I take 2 common, I get LB plus BH plus LH, which gives me the area of the total surface area of the cuboid is 2 times of LB plus BH plus LH, and the lateral surface area of a cuboid is 2H into L plus B, is how I understand the LSA and TSA of a cuboid. Similarly, when I want to find the volume of cuboid, it is nothing but is always area of base into height, which gives me area of the base is LB and height is H. Therefore, area of base is length into breadth and the height is H. Therefore, volume is LBH unit cube, and surface area is LSA with this and TSA with this unit square, is how we understand the cuboid, LSA, TSA and volume respectively. Now coming to the cube. What is a cube and how is a cube different from the cuboid? Now next comes the cube. What is the difference between a cube and a cuboid, which are taken in its shape? In this case, we say that the cube and a cuboid have their own definitive meanings, because in case of a cuboid, the length and the breadth and the height are with different dimensions, but in a cube, each of length, breadth and height are same. Therefore, in case of a cube, where I have the figure in this manner, where each of the length is L, L and L, I have the cuboid reduces to a cube if L is equal to B is equal to H. Therefore, if I derive the formulas for cuboid, then the respective formulas for cube would be nothing but when I substitute L equal to B equal to H. Therefore, let's see how we can derive the formulas for a cube with length, breadth and height, each being equal for a cuboid. So in this case, LSA of a cube is nothing but as similar as this, but 2H into L plus B, which on simplification gives me H and B are equal to L. So in place of H and B, I substitute L. So 2 times L plus L plus L, 2L into 2L, which is 4L square, is the lateral surface area of a cube. Just when I substitute B and H for L in the given formula for cuboid. Similarly, when I substitute for B and H as L in total surface area, let's see how I get a cube total surface area. So TSA is clearly 2 times of L into B is L square because I already have this to be B equal to L. So I get each of them as L square plus L square plus L square, that is 6L square. 3 times of 2, which is 6L square. Therefore, the lateral surface area is 4L square and the total surface area is 6L square, each with their lateral and total surface areas. Similarly, let's see how the volume reduces when B and H are reduced for their volume. Therefore, my volume of cube is nothing but L times L because B and H are L. Therefore, this reduces to L times L, which is L cube unit cube, is how I get the volume of the cube. Therefore, a cuboid and a cube have their own respective formulae with their respective dimensions, a cube and a cuboid as a solid structure.